Our next topic and our next speech and keynote will also be about federated learning, about vertical federated learning across the value chain. Our next speaker is already with us today. It's Michael Kühne-Schlinkert from Katulu. You have more than 20 years of experience in software engineering and product development, as well as having built several companies as a serial founder. And before you start, we read about your vision, and I want to share that because I really love that. It's your vision to make data sovereignty the key to digitalization and machine building. So maybe you'll also talk about that. So we're excited to have you here the next 20 minutes. The stage is yours. Thank you very much.
Thanks for the introduction. Yeah, it's great that we have so many talks today on federated learning, so that makes it actually super easy for me because you know already some experts. We would like to dig now more into depths to really talk about the specific case of federated learning in a value chain. And when we speak about federated learning, the key problem, what we see, and we try to give it a name, and because people know, oh yeah, I don't have data, and I can't really do machine learning. We call this the distributed data dilemma. I know that I need data I cannot access, and this is in particular the case when it comes to processes, when it comes to value chains, supply chains. All these things are super complex, and they barely involve just one company. Those usually involve multiple parties, and that's what we're going to talk about now. So when I do not have the data, I don't have a solution, and that's what we're about to change. Just quickly want to touch on horizontal federated learning, just to differentiate a little bit from vertical. So some talks you've heard more tackling the horizontal case. Horizontal is basically everyone is doing the same. So everyone is doing the same. For instance, everyone is producing PET bottles. So they basically producing the same. They're doing the same process step, and the same kind of data gets out of this process step. When it comes to vertical federated learning, it's different. Everyone is doing something different. So basically, when we stick with the PET bottles, maybe the first one is producing the bottles, the next one is packaging it, and then the last one is shipping it. So we have kind of a process chain where we basically apply federated learning and try to basically find a way to connect all these dots, all these process steps without any changing any kind of data. And when we look what this means from data perspective, in horizontal we say we have same features, different samples. What this actually means is we have basically on the same kind of data, same data points on different items, so different items that we produce, and we stick to the PET example, just multiple companies who are producing PET bottles. Unfortunately, in this setup, we usually have the case that we also have to deal with competitors, which from our experience makes it sometimes a little bit tricky. Luckily, that's not the case with vertical. When we go vertical, we're in a process, everyone has the same interest. We basically doing different steps. So we, for instance, have data on the material because we produce the material, and then we basically apply it in the process step. So we have different data sets on the same item. There are quite some challenges when it comes to vertical federated learning. That actually makes it quite tricky to bring it from research to the real-world use case. And there are a lot of research going on. I have the feeling that every week there's a new paper coming out. But from our practical experience, the thing is that value chain usually has more than 2 steps. It's quite complex, and it's not really that we have this one unique identifier that goes through the whole chain. We have maybe from the first 2 or 3 parties, we have one identifier which we can use and say, hey, this is basically what identifies our process, and then we need to think of something else, how we can really find the way to trace something through our whole process, and that makes it fairly difficult. And the data is super, super different, and we have kind of the difficulty to find a way to really apply them together in a way that makes sense. And that's basically what we want to do. I would like to bring in just some quick views on vertical federated learning, since the way we apply it is a little bit different from what some of you might have found in some papers. The simple way where vertical federated learning is coming from, and that's what's familiar from the MIT, is something that's called more split NN, and that's basically just you simply slice a model in half. you slice a model in half and you do one part of the model, you compute it as a client, the other half of this model you compute somewhere else, maybe at the server, and like this you can distribute, for example, load, and you can also distribute somehow the data in a way that you ensure privacy. With this approach here, we still have the case that the server owns the labels. That's something what we can easily solve by simply keeping them with the client and doing some more slices here, and simply slicing our model in even more halves to just do some additional computes on the server. And that's something what you can basically play infinite. So that we can basically slice a model as you want, and you can basically imply this. If we really would like to apply this to process, we need to think a little different, and that's something where the U-shape is coming in. When we speak of having multiple clients who have data on, or basically different data on the same item, what we then bring together on the server, and then combining these kind of layers. And that's the shape what we use as a foundation for the way how we do federated learning. And I would like to take a look at a use case what we applied in practice, what we call producer model. Basically, to simplify producer model is we would like to find the best way to produce an item. And for this, we basically would like to have a model from our customer who in the end would like to apply our product, our part. And if we have a model of this end product where our part will be applied, we can basically identify how our product must behave and ensure that we manufacture the exact right quality. And a huge problem in manufacturing is usually we produce a too good quality. That costs us energy, it costs material, it costs man hours, and in the end it lowers our margin. But if we produce something that doesn't suit this quality criteria, we in the end have other problems. So therefore, we would like to apply the right quality. And for this, we need some information about other process steps, because it's not that we basically own the whole process. When we produce parts, we have usually material that we apply. And when we stick with this example here, we have usually multiple suppliers that provides material. And these kind of suppliers, when we stick with plastic, they have not a consistent quality in the material. Makes it a little bit tricky to have a consistent product, what we want to create of this. So we need a model, which basically helps us to decide how we need to apply this certain batch of this model and create the best product out of it so that in the end, our end customer is happy. And that's actually what we are doing. And how we do this, that's an important point. In this kind of setup, we have some passive and active parties, and that's a setup what you usually have in vertical cases. So the passive parties are there, basically the ones who just providing data. And so they're basically passive participants in the value chain. They provide data, and the active parties, they basically use the data. They also provide data, but they also have the labels, so they basically know what the data means and can interpret the data. And basically are the ones in the end that apply the model and benefit from the model. But there are also some nuances to that that you can, we'll speak about later, and theoretically everyone can be packed as passive and active, but that's another layer of complexity. Let's get started with this one. When we would like to apply this setup in practice, it's not the case that the recycling company talking here directly to our product manufacturers. This means that they basically send directly the layer. That's something what we can do, but the one who basically work with some models, in the end you can do some reverse engineering of the layers. So I would like to avoid that I give them directly my layers. I would like to ensure that they are secure, that there's no reverse engineering possible, and that no misuse is done. So therefore we need a neutral party in the middle. And so we train and model our material behavior, and our neutral coordinator, the neutral party in the middle, that's is adding some privacy to ensure that we cannot reconstruct the original data what we use to train this kind of model. And then our manufacturer or parts manufacturer is applying this model. So he trains also a model on the quality of his parts and then applies this model. And in this case, we have a little bit a tricky situation that we need to differentiate between who is training the model and who is applying the model. What we do so far is that the training is basically decentral. So everyone is basically training their own layers of the model. But the inference, how we apply the model, is in the end centralized at the active party. It's not ideal, but the thing is otherwise, when you would like to apply the model, you need to ensure that every other party in a supply chain, in the value chain, is available and can basically do the compute. This creates latency, and this is, of course, also a risk what you have when you would like to apply this in production. So therefore, we basically apply the model directly at the active party, but we basically encapsulate it within our client to avoid reverse engineering of it. From a layer perspective, it basically means similar to the shapes of what you've seen before. We do not basically send the data from the active party to the server, because only the active party in the end needs the whole model and needs to basically compute the rest of the model. And like this, we also basically ensure that not so many parties basically have the complete model to also avoid any attacks or anything on that, and improving security. And also only our active party here has the labels. From data perspective, this simply looks like this. We need to also basically identify where we have kind of intersections between all these. Surprisingly, but the private should be crossed out actually. So the thing is, we need to basically identify here an intersection between these kind of sets of the data of the recycling company of the manufacturer, and when you work with sensitive data, and this kind of identifier is basically kind of a full name or basically a social security number, you would like to basically do this private. In this case, we basically delegate it, but not do it in a private manner. Of course, I mean, it's a batch ID of a material batch. That's nothing that needs to stay private. We do this private set intersections in another use case where it comes to actual personal data. Let's move further. So when we simply add the additional party, the recycling company is also training its layers, and then the neutral coordinator becomes an additional task. The neutral coordinator is also combining all the layers and then adding the privacy. Means that we have multiple layers, combined multiple cut layers that basically passes the inputs there, and then the parts manufacturer only gets basically a layer which combines all of these previous layers, and a lot of privacy added, so it's quite difficult to do any reconstruction there, but they can use the data of their suppliers, which is great. From data perspective, not so much a change, but I think what's important to highlight, so we from the supplier perspective, so the recycling companies here, they have different data sets. So the data sets don't need to be the same. So they can have some maybe have just some information on viscosity, some on yield points. Doesn't matter. In the end, what's important is that we need to find a way that we boil them down to having, in the end, the same features, and basically that's something what we can basically define then on the layers. But it's absolutely fine if we have different modalities of the data. That's something what's different when it comes to horizontal federated learning. Horizontal, we basically need to have really consistent, really comparable data sets there. And yeah, the last step is basically we add also our customer and let our customers train a model on the behavior, how our part should basically behave within its product, so that we can anticipate what kind of quality we actually need to produce. And that simply extends our model and makes it a little bit more wide, but in the end, it's basically the same principle. Also from data perspective, not so much a change, but that's one important point. What I highlighted in the beginning, we cannot have one single identifier. We have here basically a cut, and we need to basically also think, okay, how we can basically make the shift from having a batch IT to having a full product. So means we need to also bring these kind of multiple parts together, and that's something what we quite actually. This process in reality goes actually further, and that's something where we basically in the end have 3 or 4 shifts where we basically need to bring different identifiers together, and that's what's happening here at the Neutral Coordinator. I think a valid question is what are the participants getting out there? Why should they actually participate? And I think that's an absolutely valid question. And the first thing I think a lot of people would disagree, but from our experience is that just giving the money is completely overrated. We ask a lot of people we are working with, a lot of customers, and what's actually way more valuable if you basically enable them to make their product or their service way more valuable. So more valuable and more than just what money can actually help them. Money is something what they can, of course, apply and can make, and it's helpful, but if they can have a product offering that's actually way more stronger, or if they can be also be passive inactive, then they can also participate. Or even better, that the motivation comes out of the whole chain, where you would like to improve the whole cost efficiency or the whole footprint. That's something what can be also only done together. To apply it in practice, well, there are quite some open source frameworks out there. They're all quite research heavy, and actually it lacks a little bit on maturity, so that makes it actually tricky to apply it. There's not really a standardization when it comes to applying vertical federated learning, and there are not really good data sets out there. That's actually, maybe some of you know MNIST. There's a vertical federated learning version of MNIST, but that's nothing what really reflects reality. So it ends up where we are right now. There are a lot of proprietary solutions. We are one of them. And that's a few that you find out there that are able to apply this in practice. And that's basically what we are doing. We basically make this applicable, taking out all the complexity and make it quite easy to apply this, and that you just need to find your participants who would like to provide the data and solving your problem. That's it. Thank you.
Yes, thank you very much for sharing your insights on this topic. Again, we have a couple of minutes left, so if there are any questions from the audience. Okay, I'll look at you, maybe in the front, and then the man in the green shirt. And please quickly say who you are and what company you're representing.
Hi, Vishal Kumar from Alice Camera again. Mm-hmm. So when you cut the model and you have 2 client models that are running on the server model, what's the cost of doing that? Do you lose accuracy, or is there some engineering costs of doing that, or is it actually an optimization? Does it actually improve the overall process?
That's a good question. I mean, the thing is that you usually would not have access to this data, so that's usually the thing when you look at federated learning in general, that of course when you have everything centralized, it makes your lives easier, and you maybe even also get a more accurate model, but this is usually not the reality. So means that you will not have the case to have all this data centralized. So the opposite is to say, okay, I accept that I have this data distributed, makes my life a little bit more tricky to train the model, but like this I have a more large and diverse data set, which enables me to create a model that is less biased.
And then we have the next question over here.
Yeah, hello, this is Alexander Friedrich from Software AG. How do I have to imagine passive parties without having access to the labels participating in training the model? So question is, what is the model trained on then when not on the label output? So is it trained on some fraction of the label output, or on what else?
There are multiple approaches to that, so you can rather start with having one model that you one full initial model that you then slice, which you train at the neutral coordinator, and then basically slice in half and tell basically the passive party, you now basically file your or channel your inputs, your data into this, or you basically need to be quite specific in your cut layers and then letting them basically work against these kind of layers. It's also possible. I mean, in the end, the labels basically give the data some meaning, but when you have some specific idea what you would like to train with these certain layers, it's also working with that.
Okay.
Yeah.
Right. Does that answer your question?
Partly so. Is it? Do I? So it's. When I think of training, I think of the neurons in the network are trained on correlations between the input features and how they correlate to the actual output, which usually is labels. And I did not fully understand the answer how those. Which is trained without labels, then in the end translate into labels, or is it some fraction value which then contribute to the value altogether? That's the tricky part. So that would be an option, but as we do it currently, it's that we basically start with an initial model that we then that is basically the foundation, what we trained at the neutral coordinator, split it, and then let the parts of this initial model be fed by the data of this specific party, and then it will actually derive and get and improve. So this kind of splitting and training decentralized it's something what we're also still experimenting. What's basically the best approach to basically train a completely decentral. Also the basic development of the model and not just the training, basically.
Thank you very much. And with this, our time is up. Thanks for taking your time to answer the questions, and thanks for joining us today.
Thanks for having me.